Hi friends, are you ready to dive into the world of friction? Because we are going to look at friction in a simple and practical way in this video. I'm going to discuss the different types of friction like static friction, sliding friction, rolling friction, and we'll also look at the inclined plane here. So we are going to discuss these concepts in a very simple way, and I'm going to make the concept super easy for you so that you'll have no friction in understanding friction. So let's get started. Before we begin, I'd like to let you know that we have full courses on science, maths, coding and artificial intelligence on our website and Android app Manocha Academy. I'll put the links below, so do check it out and share it with your friends. All right, let's get started. I have this box here on the table. When I apply a small force, the box does not move. Why? Because there is a force of friction that opposes my force. Now I need to increase my force to overcome the force of friction. And now you can see the box starts moving. Is there friction when the box is in motion? The answer is yes. Because if I stop pushing the box, see, the box comes to rest due to friction. So friction is a force that opposes the tendency of motion or the motion of a body. Since motion is always relative, it's better if you remember it as friction is a force that opposes the tendency of relative motion or the relative motion of a body. Friction is a contact force. So there should be contact between the two surfaces, like the table and the box here. Now, what is the direction of friction? Friction always acts in a direction that is opposite to the relative motion, and it is tangential to the surfaces in contact. So when I try to push the box like this, the force of friction acts in the opposite direction and in a tangential direction, that is along the surface of contact. And now when the box starts moving again, the friction acts in the opposite direction and in a tangential direction. So we know that there is a force of friction on the box. But is there a force of friction on the table too? So when I push the box, does the table also feel a force of friction? The answer is yes. From Newton's third law, we know that to every action, there is an equal and opposite reaction. Forces always occur in pairs. The table is also in relative motion with respect to the box. So there is a force of friction on the box due to the table, and there is also a force of friction on the table by the box. As we discussed, friction force can be there when the body is at rest and when the body is in motion. When the body is at rest, it is called static friction. And when the body is in motion, it is called kinetic friction. Let's analyze this with our box example. When I apply a small force on the box, there is a tendency of the box to move, but the box does not move. The friction force here is called static friction, and it acts before the body starts moving. So it is called static friction because the box is at rest. The word static means at rest. Static friction is denoted as Fs. Now, as I increase my force on the box, the static friction automatically increases to oppose the motion because its job is to keep the box at rest. Static friction is cancelling my force here. Now, as I keep increasing my force, static friction reaches its maximum value. And if I continue to increase my force, the box will start moving. The maximum static friction force that comes into action just before the body starts moving is called limiting friction. Limiting friction can be denoted as Fs max, or you can write F limit. So static friction Fs is always greater than or equal to 0 and less than or equal to the limiting friction Fs max. Static friction is a variable force because it self-adjusts itself to match my applied force, trying to keep the body at rest. When you push a heavy box, you must have noticed that initially you need to apply a large force to get the box moving. But once the box is in motion, you need to apply a lesser force to keep it in motion, right? Why is this? This is because the kinetic friction is less than the limiting friction. The force of friction that comes into action when the body is in a state of motion is called kinetic friction. Kinetic means motion. That's why it is called kinetic friction. Kinetic friction is denoted by Fk. Kinetic friction Fk is less than the limiting friction Fs max. Kinetic friction is a constant force. So once the body is in motion, the kinetic friction does not depend on the applied force or the speed of the moving body. Now, if you draw a graph of friction versus the applied force, it's going to look something like this. As we apply the force on the body, like the box here, the static friction force will match our applied force. That's why you can see the graph is a straight line. Since when the body is at rest, static friction equals to my applied force. But static friction can increase only up to a certain maximum value. That is called the limiting friction. So if the applied force is greater than the limiting friction, the body starts to move and the friction force will now reduce. Now once the body is in motion, the friction force is constant. And that's why the graph is a horizontal straight line like this. Now let's discuss the formulas to calculate static and kinetic friction. We will start with static friction. As we discussed, static friction is a variable force. It is a self-adjusting force that has a range of 0 to the maximum value called limiting friction. Now, based on experiments, the scientists found that the limiting friction does not depend on the area of contact. So it does not matter if the box is placed like this with a large area of contact, or if you place the box like this with a smaller area of contact. The static friction, the limiting friction will remain the same. So static friction is independent of the area of contact of the box. Static friction depends only on the nature of the surfaces in contact and the normal reaction between the two surfaces. For this box, the normal reaction will be equal to the weight of the box, because the box applies a force of weight on the table, and in response, according to Newton's third law, the table applies a normal reaction over here. But note that limiting friction depends on the normal reaction and not the weight, since there could be other forces affecting the normal reaction. For example, if I press the box like this, then I'm increasing the downward force on the table, so the normal reaction is going to be larger. So remember, static friction, that is the limiting friction, depends on the normal reaction, not on the weight. The limiting friction Fs max is directly proportional to the normal reaction. So we can denote it like this: Fs max directly proportional to N, the normal reaction. Now we can change this directly proportional relation into an equation by writing Fs max equal to mu s N, where mu s is the constant of proportionality and it is called the coefficient of static friction. Note that this is the formula for the maximum static friction, which we call as limiting friction. Static friction is a variable force, so static friction does not have a formula. It ranges from 0 to Fs max, but the maximum static friction Fs max has this formula, which is mu s times the normal reaction. So let's understand this formula with an example here. Let's say the mass of this box is 1 kilogram. So what is the weight of the box on the table? That's right, you can use the formula W equal to mg. The weight is going to be mass 1 kg times the acceleration due to gravity 10 meters per second square. So the weight of this box is 10 Newton and it is applying this weight on the table. It's the force on the table. So what will be the normal reaction of the table on the box? That's right, it's going to be same as the weight here because there are no additional forces. So it's going to be 10 Newton. Normal reaction is equal to the weight here. Now let's see if we can calculate the limiting friction, the maximum static friction. Let's say the coefficient of static friction is 0.3. So mu s here is 0.3. So what is the limiting static friction going to be? Fs max will be 0.3 times the normal reaction, which was 10 Newton. So Fs max is 3 Newton. That means the maximum static friction, the limiting friction here is 3 Newton. This means if I try to push this box, what is the force that I need to apply? That's right, I need to apply a force greater than 3 Newton because less than 3 Newton, static friction will not allow the box to move. Only when my force becomes more than 3 Newton, the box starts moving. So this is how we can apply this formula to calculate static friction. Next, let's look at kinetic friction. The friction when the body is moving. Now, based on experiments, the scientists found that kinetic friction does not depend on the area of contact or the velocity of the moving body. Kinetic friction depends only on the nature of surfaces in contact and the normal reaction between the two surfaces. We can write the kinetic friction Fk is directly proportional to N, the normal reaction. Once again, we can change this directly proportional relation into an equation and write it as Fk equal to mu k times N. Now mu k here is the constant of proportionality and it is called the coefficient of kinetic friction. As kinetic friction is always less than the limiting friction Fs max, so the coefficient of kinetic friction mu k is always less than the coefficient of static friction mu s. Now let's understand this equation here with an example. So once again, the mass of this box is 1 kg. So what is the normal reaction here? For that, we have to again calculate the weight of the box, which we looked at was 10 Newton. You just use the formula W equal to mg. So 1 kg multiplied by the acceleration due to gravity 10 meters per second square. So the weight was 10 Newton. So what is the normal reaction on this box? That's right, it's going to be 10 Newton. So when I'm pushing this box, what will be the kinetic friction here? You can calculate it as mu k times N, the normal reaction. Now let's say the mu k value here is 0.2. See, it is less than our mu s, which was 0.3. So what will be the kinetic friction force? It's going to be mu k times the normal reaction N, which means 0.2 multiplied by 10 Newton. So our force of kinetic friction is 2 Newton here. So this is how you can use the formula to easily calculate the kinetic friction force. That is the friction force when the body is in motion. Now let's look at the concept of angle of friction. Let's say we are applying a force on this box and it is just about to move, but it still hasn't moved. So what is the force of friction here? That's right, it will be the maximum static friction force or the limiting friction since the body is just about to move. Now this friction force is along the tangential direction in the opposite direction to my force here. The box also experiences a normal reaction force by the table which is in a perpendicular direction as shown here. Now as you can see, there are two contact forces on the box, the limiting friction force and the normal reaction. So what will be the net contact force as a result of these two forces? That's right, it will be in this direction at an angle to the normal reaction. This angle between the resultant contact force and the normal reaction is called the angle of friction. We can denote it by the symbol theta as shown here. Now using trigonometry, we can write tan theta is perpendicular divided by base. So it's going to be the frictional force, the maximum limiting friction force here, divided by the normal reaction. So tan theta is going to be equal to Fs max divided by N. As we discussed, the formula of limiting friction is Fx max equal to mu s times the normal reaction N. So substituting this in the formula, the normal reaction N is going to cancel. So what are we left with? Tan theta equal to mu s. That is, the coefficient of static friction is going to be equal to the tangent of the angle of friction. So let's say the angle of friction is 30 degree. So what will be the coefficient of static friction? It's going to be equal to tan of 30 degrees, which is 1 by root 2. And that's equal to 0.5773 or approximately 0.58. So remember, what is the angle of friction? It is the angle made by this resultant contact force with the normal reaction. And the resultant contact force is the result of two forces. The tangential frictional force, which is the limiting friction here, and the normal reaction. And note that this angle of friction is used only when we have this limiting friction. That is, the body is just about to move. So that is the maximum static friction. We have looked at the angle of friction. Now let's look at the angle of repose. For the angle of repose, we need an inclined plane. But unfortunately, this table is flat. I need an inclined plane now. So for that, I'm going to use this box that I got from YouTube. They had sent us this gift. So I'm going to use this box as an inclined plane here. So I'm going to place it like this. And we'll take another smaller box here and place it. Now, how do I get the inclined plane? I'm going to slowly lift up this box like this, as you can see here. Now, if I keep increasing the angle of inclination, which is the angle of the inclined plane, you can see that this small box is not sliding down. But if we keep increasing it, there will come a time when this box just starts to slide down, as you can see here. Can you see it's moving? So this is the special angle where this angle is called the angle of repose. So let me bring this box back, because actually the small box should not be moving. Okay, it should just begin to slide down at the angle of repose right here. So this is the condition we are interested in for the angle of repose. Angle of repose is defined as the minimum angle that an inclined plane makes with the horizontal when a body placed on it just begins to slide down. Let's label the angle of repose here as phi. Now, if this box is of mass m, then its weight is going to be mg, which acts vertically downwards. Now, using geometry, you can see that phi is also the angle made by the weight mg and the perpendicular component of the weight on the inclined plane. Now, using trigonometry, let's break down the vertical weight force into two components. So we'll break down mg into mg cos phi, which is perpendicular to the inclined plane, and mg sin phi, that is along this inclined plane. So when the body just starts to move, the limiting friction Fs max equals mg sin phi. These two forces balance each other. Since the perpendicular force by the box on the plane is mg cos phi, the normal reaction of the plane on the box n is equal to mg cos phi. So now let's use the limiting friction force formula. Fx max equals mu s times n, the normal reaction. So that's going to be mu s times mg cos phi. So substituting Fs max equals mg sin phi, we get mg sin phi equal to mu s mg cos phi. Now you can cancel the mg on both sides of the equation, and we are left with mu s equal to sin phi divided by cos phi, which is equal to tan phi. Now we also know that the coefficient of static friction mu s is equal to tan theta. Remember, where theta is the angle of friction. So what are we getting? mu s equal to tan theta equal to tan phi. So tan theta is basically equal to tan phi. That means theta, the angle of friction, equals phi, which is the angle of repose. So remember this important relation that the angle of friction is equal to the angle of repose. And remember, angle of repose is with reference to this inclined plane. When the body just starts to slide down like this, right? So when it just begins to slide down, we consider this phi as the angle of repose, and theta was the angle of friction, which we had discussed earlier. Both these angles are equal. Kinetic friction is of two types, sliding friction and rolling friction. When there is sliding motion, like this box sliding on the table here, the force of friction is called sliding friction. When there is rolling motion, like a ball rolling like this or a wheel rolling on the surface, the force of friction is called rolling friction here. For the same normal reaction, rolling friction is much smaller than sliding friction. You have seen that it is much easier to push the box when it is on wheels than to push it in a sliding way. Let me try it out here by using these pencils. So I'm going to make wheels out of these pencils. We'll put it under the box here like this. So when I place the box on pencils like this, you can see it is so easy to move the box. It is so smooth, right, as compared to the sliding friction. Why? Because rolling friction is much lesser than sliding friction, as you can see with the movement here. Why is rolling friction so less? When a wheel rolls without slipping, the surface in contact do not slide over each other. If there is no slipping, the relative velocity of the point of contact of the wheel is zero. So in the ideal situation, there is no sliding or static friction. In reality, as the wheel rolls, it exerts a large pressure on the road due to the small surface area. Because remember, when it is rolling, the surface area of contact is very small. This causes a slight depression of the road below and a small elevation or bump in front of the wheel. So the rolling wheel has to overcome the bump in front of it when it moves ahead. This is the cause of rolling friction. Experiments on rolling friction have shown that rolling friction is directly proportional to the normal reaction, and it is inversely proportional to the radius r of the rolling wheel. So if we combine these two, we get rolling friction is directly proportional to n by r. That is the normal reaction divided by the radius of the wheel. So using the constant of proportionality, we get Fr equal to mu r times n by r, where mu r is the coefficient of rolling friction. So as we discussed, since rolling friction is less than sliding friction, and that is less than static friction, we can say that these coefficients of friction are related like this. Mu r is less than mu k is less than mu s. Note what does each one mean? Mu r is the coefficient of rolling friction, which is less than the coefficient of sliding friction, which is mu k, the kinetic or sliding friction here, and that is less than mu s, which is the coefficient of static friction. So be careful not to confuse s with sliding. S means static, k here means sliding, and r is rolling. So now let's apply this formula for rolling friction and calculate the rolling friction for a wheel. Let's say the wheel is of mass 1 kg, so the normal reaction is going to be 10 Newton, right? The weight is going to be 1 times 10 meters per second square. So the weight is 10 Newton, so the normal reaction will also be 10 Newton. And for simplicity, let's say the wheel has a radius of 1 meter. And the coefficient of rolling friction is, let's say, 0.02. So if you use this formula, what is the rolling friction that we get? We get 0.02, the coefficient of rolling friction, multiplied by the normal reaction, which is 10, divided by the radius of the wheel, 1 meter. So what is the answer here? The rolling friction is really small because it is 0.02 times 10, which is 0.2 2 Newton. And that is why the wheel is considered one of the greatest inventions of man, because it made transportation so smooth, because rolling friction is very, very small. So friends, let's place the summary of the formulas that we have learnt on friction on our concept board here. Here's a question on friction for you. A block of mass 2 kg is placed on the floor. The coefficient of static friction is 0.4. A force of 4 Newton is applied on the block as shown here. Now can you calculate the force of friction between the floor and the block? Do let me know your answers by putting it in the comments below, and I promise to reply to your answers. So go ahead and try out this question and let me know your answers in the comments below. Friends, hope the concept of friction is crystal clear to you now, and you will have no friction in hitting the like button and sharing this video with your friends. And if you haven't subscribed to our YouTube channel, hit the subscribe button right now and click on that notification bell so that you don't miss out on any of our videos. And do check out the full courses on our website manochaacademy.com and our Android app Manocha Academy. I'll put the links below. We have full courses on physics, chemistry, biology, maths, coding and artificial intelligence. In these courses, you're going to get live classes, interactive videos, quizzes, questions, mock tests and revision notes. So what are you waiting for? Do check out the links below and share it with your friends. So stay connected with Manocha Academy and just keep learning. And if you haven't subscribed to our YouTube channel, hit the subscribe button right now and click on that notification bell. Mane timing of bell.